Great. Thanks so much for the invitation. Thank you so much for organizing this conference. Everything has been amazing. I'm really excited to talk to you about some recent work where we use some analytical techniques to get very sharp bounds on the eigenvalues of random regular graphs. So this is joint work with Jiaoyang Huang, who's a professor at the University of Pennsylvania, and Hongsir Yao, who's a professor at Harvard. So when I was preparing this talk, I was thinking about it, and I think really an apt alternative title is this, which is How I Learned to Stop Worrying and Love the Green's Function. And the idea here is that we use these sharp analytic techniques, basically a series of matrix inverses, and this will tell us about the distribution of eigenvalues in this model. All right. So just as a very rough outline, we'll talk about the motivation, then some of the methods, and then future directions. So let's start with my motivation. So fundamentally, this is a problem about spectral graph theory. So we're interested in spectrum of graphs. Every graph is an adjacency matrix. So if I have a graph that looks like the left-hand side, I have a matrix, rows and columns correspond to vertices. I put a 1 if there's an edge. I put a 0 if there's not an edge. And it turns out that there's very nice interplay between these two objects. The spectrum of the adjacency matrix gives a very large amount of information about the geometry of the graph. And then conversely, looking at a matrix as a graph problem is a way to turn a linear algebra problem into a problem with some inherent geometry. And specifically, you can think about it as some kind of spectral geometry problem. So specifically, the model that we're going to look at is the random regular graph model. So this is something that's typically looked at if you want a sparse network that still maintains strong connectivity properties. And a generic model of this is going to be the random regular graph distribution, which I'll call GND. So the idea is that I fix the number of vertices n. I then fix the degree of every vertex, d. And then there are a finite number of graphs that are on n vertices, which are deregular. So I can just sample one uniformly at random. So this is an example of a 20-vertex, 3-regular graph. So Ramon, in his very nice mini course that he gave earlier in this week, talked about how there are many ways to generate a random regular graph. This is one of them. We can also think about this permutation model. There are other ways as well. The point is that they're all, in this analysis, they're all somewhat equivalent. So you can just choose your favorite model if you prefer another one. But for now, just think about just choosing one uniformly at random out of a bag. So the object that we're going to look at in terms of the spectrum is going to be this normalized version of the adjacency operator. And this normalization will just be convenient to compare this to different matrix models. So I'm going to look at H, which is equal to A over square root d minus 1. So immediately, thinking about the eigenvalues, well, I have a real n by n matrix. So I'll have n, which is symmetric, so I'll have n real eigenvalues. The largest one is always going to be d over square root d minus 1. So that will correspond to the all ones vector. And by the Perrin-Frobenius theorem, this will be the eigenvalue of largest magnitude. So our goal during this talk is going to give very precise information about what the spectrum of the random regular graph looks like. OK, so let's first talk about weak convergence. So once again, what was mentioned on Tuesday is that if you just look at, for example, the moments of a random regular graph, then you can see that the eigenvalue distribution is going to converge weakly to the specific spectral measure, which is known as the Kesta-McKay law, given by the right-hand side here. So if I just take the empirical distribution of eigenvalues, this will converge weakly to this Kesta-McKay law. So in the middle of the slide here, I have two plots that are superimposed on each other. The blue line is the Kesta-McKay law, so what's predicted according to this formula. And then the red histogram gives the eigenvalues of a very large random regular graph. And what we see is that these two match each other very, very closely. Right? So this seems like an effective law. There are a couple of things, though, that I want to note about this measure. So the first one is that this distribution here does not witness the top eigenvalue. Right? So we know that the top eigenvalue is always going to be d over square root d minus 1. But the point is that for now, we only care about weak convergence, so we can throw out an individual eigenvalue. And if you have good eyesight, then maybe you can see that there's a little column on the right-hand side that's outside of the rest of the spectrum. So that corresponds to this lambda 1. The second thing that I want to note is that as d goes to infinity, this will converge to the semicircular law. So if I look at this formula here, d only contributes in the central part, and as d goes to infinity, this converges uniformly to 1. So I can, for very large d, I can basically just erase this, and what I'm left with is the semicircular law. And the important thing to realize here is that there's an intrinsic relationship between the Keston-Decay law and the semicircular law that we're going to utilize in our analysis. All right, so this talks about weak convergence, but what I want to tell you now is that individual eigenvalues will be determined very strongly by this Keston-Decay law. So first, let's focus on the edge eigenvalues because of their utility in talking about spectral expansion. So the Alon-Bopana bound says that if I look at these edge eigenvalues, throwing out lambda 1, so lambda 2 and minus lambda n, these are always at least 2 minus little o of 1. And note that this is in line with what we saw from the Keston-Decay measure, right? So this is saying that my edge eigenvalues cannot be too far inside of the spectrum when I get larger and larger graphs. OK, so this led Lubotsky, Phillips, and Sarnak to define a Ramanujan graph as a graph where this inequality is true in the opposite direction as well. So specifically, it will be a deregular graph is Ramanujan if every eigenvalue which is smaller than d over square root d minus 1 is also smaller than 2, right? So there's this very large spectral gap, actually optimally large spectral gap, according to this Alon-Bopana bound. And these, once again, are of interest because they're optimal spectral expanders. They have eigenvalues which are as small as possible. So there are basically two types of Ramanujan graphs. So the first type is the non-bipartite version. So in this case, I have one eigenvalue at d over square root d minus 1. And then all other eigenvalues are in the interval minus 2 to 2. The other type is the bipartite version, where I have two trivial eigenvalues. So here, lambda 1 is equal to minus lambda n is equal to d over square root d minus 1. And then everything else is contained in this interval, minus 2 to 2. OK. So constructing these Ramanujan graphs has been a well-studied problem over the years. So in this first paper by Lubotsky, Phillips, and Sarnak, and also the same year by Margulis, they constructed versions of these Ramanujan graphs, both the non-bipartite and the bipartite case, using number theoretic techniques for when d is equal to p plus 1 for p some prime. This was then generalized by Morgenstern to d is equal to a power of p plus 1. And then later on, Adam Marcus, Dan Spielman, and Nikhil used non-number theoretic techniques to prove existence for, in the bipartite case, for any d and any n. OK, so this bipartite case, we know existence in every possible scenario. However, proving existence of non-bipartite Ramanujan graphs has remained an open problem. And moreover, any example of a non-bipartite Ramanujan graph would actually give us further examples of bipartite versions by taking what's known as the bipartite double cover as well. All right. So what about a random graph? So let's go back to the random regular graph. Nogel alone conjectured that with high probability, if I take a randomly sampled graph, then it will be almost Ramanujan. So what does this mean? This means that lambda 2 and minus lambda n are at most 2 plus some factor that goes to 0. All right, so this was an open conjecture for many years. And then it was proven by Joel Friedman, who used this very delicate trace argument and showed that, in fact, lambda 2 is at most 2 plus something like 1 over polylog n. And this was given an alternative proof that was a bit shorter by Charles Bordunov later on, also using tracial methods. So after this, my collaborators, Jiaoyang Huang and Hongsu Yao, improved this to 2 plus 1 over polynomial in n. And actually, they showed something stronger, which is that if I look at any eigenvalue besides lambda 1, we always know where lambda 1 is, so let's just ignore it. So if I take any other eigenvalue, and I look at where I would expect it to be, the difference between those two is at most this same bound of O of n to the minus 1 over 100. Now, where would I expect the kth eigenvalue to be? Well, we can think about this as, for my kth eigenvalue, I would expect 1 minus k over n of my spectrum to be to the left, and then k over n of my spectrum to be to my right. Right? So to say this for the Kesta-McKay law is that when I integrate according to the density of the Kesta-McKay law, then at gamma k, where I would expect it to be is when this integral is exactly equal to 1 minus k over n. So this is like where I would expect lambda k to be, and they show that it fluctuates in some polynomially small interval there. OK, so this is state of the art, let's say, before 2024. But what would we actually expect to be the real answer? Like, how big should this fluctuation really be? Well, Miller, Novikov, and Zabelli ran these computer tests. And what they observed is that lambda 2 and minus lambda n seem to converge to Tracy-Whittam. So the distribution of the largest eigenvalue of a GOE matrix. And so this is a plot from this paper where up to some normalization, it seems like you're getting the same distribution. So specifically, this led them to conjecture, which was also put forth by Peter Sarnak a couple of years before as well, that if I look at lambda 2, I normalize by shifting it to, by subtracting 2. I then multiply by C1 times n to the 2/3, and then I do this other shift, then this will converge to Tracy-Whittam for some values of C1 and C2. So I'll just note that this is known to be true if D is allowed to grow polynomially with n, both in the regime where D is less than n to the 1/3 by these two works, first shown in a smaller regime by Bauer-Schmidt, Knowles, Huang, and Yao, and then later by Huang and Yao for this entire interval, and then also for when D is bigger than n to the 2/3 by Yuke and He. So if we want to do this, though, for D is a constant, right, and moreover, if we're able to show this where C2 is equal to 0 and these edge eigenvalues are independent, then what this would actually mean is that about 69% of graphs are Ramanujan. So this thing that's been very hard to find is actually quite common in the sense that a majority of graphs have this property. Now, why 69%? Well, this is just the probability that this Tracy-Whittam distribution is less than 0, and it's that squared, right? One for lambda 2, and then the other one for lambda n. So another consequence of this conjecture is that the fluctuation of lambda 2, like the true fluctuation should be like n to the minus 2/3 plus little o sub n of 1. And note that this type of Tracy-Whittam statistics is very different from what we get for Erdős-Renyi in the constant degree case, where we see very different behavior, I'll just say. OK, so let me say the first result, which is that, first of all, just in terms of the implication, that the fluctuation of lambda 2 is at most n to the minus 2/3 plus little sub n of 1. But more generally, what we show is that if I look at the difference between lambda k and gamma k, once again, you can throw out lambda 1 because we always know where it is, then it's going to be very, very close to where I would expect it to be. So specifically, the fluctuation is like n to the minus 2/3 times this other factor that gets bigger the farther into the bulk I get. So at the edge, I get n to the minus 2/3 plus little of 1. And in the, for example, for lambda n over 2, this fluctuates at like n to the minus 1 plus little o of 1. OK, so just to compare, so first of all, this is the optimal rate of fluctuation. It matches the GOE for every eigenvalue, and also it matches this conjecture. Huang and Yao had previously achieved this n to the minus 1 over 100. And then I also wanted to, of course, mention this very nice result by Chen, Garza Vargas, Trop, and Van Handel. So they proved a statement about much more general families of random graphs. But specifically, when you apply it to the random regular graph, you get a very short proof that these edge eigenvalues are at most 2 plus n to the minus 1 over 6. Once again, this generalizes in a lot of different ways that our result definitely does not. And also, this is a much shorter proof as well. So yeah. OK, and then our second result is that we actually prove this conjecture. So we show that for every d, if I renormalize by this constant here, so I take n times this constant, I then raise this to the 2/3, then this converges to Tracy Whittam 1. And the same is true for minus lambda n. And in fact, these two are independent. OK, so where does this constant come from? It's actually quite natural, because this gives the ratio of the density of the Keston-McKay law and the semicircular law at the edge. Right, so the order of fluctuation is going to be proportional to basically the gap between lambda 2 and lambda 3. And the point is that this is the ratio of the gap between these. OK, and so indeed, this proves this corollary, which is that a majority of these of d-regular graphs are non-bipartite Ramanujan. So these edge eigenvalues are less than 2.
Sorry, you have two pictures. Like one of them is a mesh. What is the second one?
These two pictures?
Yeah, the right is.
OK, so this is the unnormalized version, and this is the normalized version. Right? So these are the same two plots, but just normalized so that the coefficients, just so that they have the same mean and variance.
Just saying that really you need normalization. That's what
Yeah.
Can I make a cultural observation?
Sure.
It's customary to say that Ramanujan graphs have the best possible spectral gap. But your result disproves this, right? Because more than half of the eigenvalues are actually even less.
Sure.
Rounded away from 2 at the scale and to the natural scale n to the minus 2/3.
Yeah.
In some sense, I interpret your result as saying that there's nothing special about Ramanujan graphs. There's some arbitrary choice.
Yeah.
Obama says that it's lower bounded by 2 squared d minus 1 minus little o 1. So the inverse of that is plus little o 1.
Yeah.
Right?
Yeah.
Which constant doesn't matter?
Sure, that's fair. I mean, yeah, I've heard this term being thrown around of like super Ramanujan graphs, which beat this. I mean, like the this Markin-Spielman's Rasa result, you really get 2 minus O of 1 over n, right? Yeah. So yeah, but yeah, this is saying that you can, at least for a typical graph, you can get even a little bit less, like n minus n to the minus 2/3. So yeah, it is interesting. Any other questions about the results? Yeah. Oh. All right. So I might as well get to that then, right? So we'll talk specifically about our methods now, and big picture. We'll talk about doing Green's function analysis, some of the ways that we maneuver through this probability space, and then also these Schwinger-Dyson equations that we utilize as well. All right. So let's get to the Green's function. So a common way of finding spectral information is to calculate moments, right? So I take the trace of high powers. The thing is that, so moments can be easy to calculate, but oftentimes what you get is information about the largest eigenvalues. And oftentimes that's actually not sufficiently precise in terms of what we're looking for. So what we do instead is that we look at the Green's function. So what we do is that we take a complex number with positive imaginary part, and then we take our operator minus z times the identity and invert it. So the point is that this inverse exists, right? Because H has real spectrum, right? And Z has positive imaginary part. OK, so what can this tell us about the spectrum of our matrix? Well, I can look once again at the normalized trace, which I'll call the Stilches transform. And it's just the 1 over n times the sum of diagonal entries. And if I just view that in terms of eigenvalues, that's like taking 1 over n times the sum of lambda I minus z quantity inverse. Okay. So we can think about this as some kind of discrete integral. So for a more general spectral density, I can also take the Stilches transform, which will be integrating over R this density divided by x minus z. OK. So what can this tell us about the spectrum? Well, if I look at the imaginary part of the Stieltjes transform, this is going to be some approximation of the indicator of how many eigenvalues are in a certain window. Specifically, let's set z equal to e plus I eta. And what the imaginary part of the Stieltjes transform approximates is how many eigenvalues are of distance at most eta from E. So really what it tells us, what it is a smooth version of this given here, right? But the point is that this is going to blow up if the distance from E is less than eta, and it will be small if the distance of E is greater than eta. This is a smooth version of this. And so what we would expect is something that looks like this, where if I fix eta and then vary E, then I'll get a blow up of width approximately eta every time I see an actual eigenvalue. OK? So what I want to do is I want to compare these two Stieltjes transforms. So I'll take the one that's associated with the infinite tree, which I'll call MKM. And then what I want to show is that the Stieltjes transform of my random regular graph converges to that of the infinite tree. So if I were able to do this for eta constant, this would give weak convergence. So this would give this type of moment convergence that we saw before. However, if we can show it for eta all the way down to n to the minus 1, this would give convergence of individual eigenvalues. And note that actually eta equal to n to the minus 1 is actually optimal, because I can't approximate a discrete distribution with a continuous one at intervals of length less than 1 over n. Right? So really, this is saying I have optimal approximation between these two distributions. And really what we show is that we show a more complicated statement, but an example of the type of statement that we show is that specifically when E is small, or smaller than 2, then with high probability, these two approximate each other to the level of n to the epsilon over n eta. So n eta is 1 over n eta is like optimal. And basically for any constant epsilon, we can get within n to the epsilon times that optimal rate. All right. So let me just take a step back, and I'll give like a big picture of like how do we think about the Green's function in our analysis. Well, I think there are basically two main ways. So the first way is that you can think about it as some kind of walk generating function, right? So the Green's function is equal to minus z times I plus h. I just reordered it. And then I can expand this into powers of h. And the point is that these are just given some complex weights. And oftentimes we'll take this interpretation because we'll think about different walks that exist on the graph, and then we'll think about the randomness associated with different parts of the graph, and therefore the walk associated with those parts. So this is quite useful. But the thing is that it's not sufficient, because we want z to be very, very small inside the radius of convergence. So that means that we use this other interpretation, which is that the Green's function is trying to solve the eigenvalue equation at this value that's not actually an eigenvalue at z. So we can think about it in this electromagnetic interpretation, which is basically the response at y given a charge of energy z at x. So this is the heat map of the Green's function for a two-dimensional lattice. And what we can see is that for the imaginary part of the Green's function, what we can see is some nice oscillatory behavior, but also some decay as well as we get farther and farther away. And the way that we use this in a quantitative way is that if I sum the squared entries along a row of the Green's function, then this is equal to the imaginary part of the diagonal entry divided by eta. So this is the type of improvement that we need over only thinking about it in this combinatorial way.
So is the Gij squared mean, so is that h?
So this is, I'm looking at my Green's function, which is an n by n matrix.
Oh, I'm sorry.
Yeah, and then I'm just summing all the entries along a row. And what I'm saying is that the sum of squared entries along a row is equal to the imaginary part of the diagonal divided by eta. Yeah. No, that's good.
Sorry, what's eta again?
Eta is the imaginary part of the Green's function. So z is equal to e plus I eta. Yeah. Okay. Okay. So, all right, so how are we going to utilize this? Well, we want to think about what makes this, the Green's function of the Keston-McKay law special. And the point is it's this relationship with a semicircular law. So specifically, I can use the Schur complement formula. The Green's function is just the inverse of a matrix. Even for the infinite operator, it's somewhat similar. And the idea is that if I'm interested in the entry of my inverse, it's just a function of the individual blocks associated with this operator. So specifically, if I'm interested in the value of the Green's function at a given vertex, then I can write it as a formula in terms of the graph after I delete the vertex, and then the neighbors of the original vertex. Right, so this leads to, I can do this specifically through this equation, and this leads to this nice formula which says I can write the Keston-McKay law in terms of this other law, MSC, which is just the root of this infinite d-1 array tree, which is just the tree after I delete a single vertex. Okay, so the nice thing is that if I do this again, then if I delete a vertex from the d-1 array tree, I'm just left with other d-1 array trees. So what this means is that the Schur complement actually just gives a formula of MSC in terms of itself, right? Which is what's known as a self-consistent equation, right? And the nice thing is that this completely defines this Green's function for any value of z. All right. So how are we going to utilize this in our analysis? Well, I think the two takeaways are that if I want to find something that looks like the Keston-McKay law, it might be easier to find something that instead looks like the semicircular law. And the other thing is that to find something that looks like the semicircular law, I want to find something that satisfies the self-consistent equation. So how did we get the semicircular law? We deleted a vertex and then looked at the value at its neighbor. So I'm just going to do that in the graph. So I have this function q, which is the average over all directed edges of deleting one vertex and then looking at the value of the neighbor. Right, and I'll just take the average over the entire graph. And what we claim is that to show approximation of the Stieltjes transforms, it's actually sufficient to show that q is approximately equal to MSC. And then in turn, to show that, it's actually just sufficient to show that q satisfies the self-consistent equation that defines the semicircular law. So really, what we spend the majority of the paper doing is trying to prove this, really a more complicated version of this, but this is pretty close, which is that with high probability, then once again, up to this arbitrarily small multiplicative error factor, I have q minus y of q is less than or equal to n to the epsilon divided by n eta, which is once again this optimal rate.
So can you explain why you expect this q term will behave like a semicircular law?
Okay.
So you need to take a d goes to infinity to see semicircle.
Yeah, but I guess the point is that if I delete a vertex and then look at the root, I can take finite d. So the semicircular law here exists for any d if I just delete one vertex. So the idea of q is to just do the same thing in the actual graph. I just delete a vertex and then look at the value at a neighbor, right? So the point is like, I agree that Keston-McKay only converges to semicircular for large d, but for example, if I take a binary tree, and I'm interested in the spectrum specifically associated with the root, that is semicircular. Yeah.
It's basically because this describes the Fock space, right? If you have two generated. That's the graph associated with the Fock space.
Okay.
Mm-hmm. For example, another way to see it is that it's defined by the moments once again, and what you can see is that now that every time I go down, I have two choices, every time I go up, I have one choice. So the number of walks that start and end at the root is going to be a Catalan number multiplied by some other factor. Yeah. Good. OK. So this is what we're going to show. So let's talk about enlarging the probability space. So what's the problem that we're trying to solve here? The idea is that we want to take the expectation of this, of moments of this really, over all d-regular graphs. But the point is that there are many such graphs, right? There are something like dn double factorial many such graphs, and the entries are not independent. So how are we going to do this? We're going to use the invariance of the distribution over random edge swaps. So if I start with some graph, I'll copy it here. I'll highlight two edges, and then I swap their adjacency. The point is that each of these two graphs is equally likely to appear in the random regular graph model. Specifically, if I have any pair of edges, it's equally likely that I see the edges like this versus like this, no matter what that is. So how are we going to utilize this? We're going to utilize this by randomizing the neighborhood of a vertex. So I start with some vertex O. I then randomly select edges. I then perform a swap on those edges. And what I get is a new boundary. So the new boundary of O is going to be the C sub alpha, which is half of the randomly sampled edges that I chose. And what we're going to do is think about the expectation of q minus y of q raised to the p by further taking the expectation of this random edge swap. OK. And what we actually have to do is iterate this process. So we're going to start by randomizing the boundary of O by choosing these other edges in my graph, B alpha, C alpha. But then I'm going to iterate by randomly sampling the neighborhood of this vertex C alpha. Right? And then I select other random edges, which will be the new boundary of C alpha. And then I'll iterate this process. And the point is that we do sharp enough analysis that we're able to iterate this process and do many edge swaps. And every time that we do an edge swap, we can actually improve the error in the function that we're looking at. So just to compare, in this previous work of Huang and Yao, they were able to take the expectation by doing one switch. And so basically, we're taking the expectation over something like n to the log n many graphs. But by doing the sharper analysis and doing this iteration scheme, we're able to sample over something like n to the n many graphs. So much closer to the true number of graphs that there are. OK? All right. And now let me talk about this Dyson-Schwinger equation. So, OK. So yeah, Vadim talked about this in the previous talk, which is good. But the way that we show universality is through Dyson Brownian motion. And the idea is as follows, is that we're going to take some kind of matrix-valued Ornstein-Uhlenbeck process. But the important thing to know is that at time t, the distribution of my matrix is going to be the sum of two matrices, one of which is my original matrix, and the other of which is a GOE. And the point is that as t increases, I'm slowly replacing my original matrix with the GOE. Right? So to prove that this second eigenvalue is Tracy-Whittem distributed, we're going to use this three-step process that was mentioned before. So the three steps are, first of all, we want to show optimal eigenvalue rigidity. So that was like the theorem 1 that I showed you guys before. The second step is that after some small amount of time, so t is like n to the minus 2/3, the graph that's distributed like this has Tracy-Whittem statistics. So I've added enough noise such that what I end up with has Tracy-Whittem statistics. So that follows from previous work of Landon and Yao. Yeah.
Is there any intuition for where the n to the minus 1/3 comes from?
Yeah. So the point is that, once again, the difference between lambda 2 and lambda 3 is something like n to the minus 2/3, right? So the point is that once I've added this much noise, because of the formula that Vadim had in his slides, which says that basically the rate of change of the eigenvalue under Dyson Brownian motion is proportional to 1 over the distance to the next closest eigenvalue. So the closer that eigenvalue is, the faster it's going to move. So what that means is that this is the amount of noise that we need to add until we actually get Tracy Whittem. Yeah, good question. OK. So the point is that this is enough. And then the last step is to show that when we've done this perturbation, we actually haven't changed the distribution. Right? So we know that what we end up with is Tracy Whittem, but we need to show that we actually haven't changed anything. And in order to do this, we show, once again, proximity of the Green's function before and after the perturbation, but this time at a tighter error, at an error that's less than 1 over n eta. OK. So how do we do this? Well, we do this with these Dyson-Schwinger equations. So like we mentioned before, the semicircular law satisfies this very nice self-consistent equation. But the point is that it's impossible for any discrete Stieltjes transform to satisfy this equation with error less than 1 over n eta. And the point, once again, is this difference between discrete and continuous spectrum. So what we're going to do is actually compare two discrete objects, right? So one is going to be the random regular graph, and the other is going to be the GOE matrix. And the idea is to think about equations which are specifically satisfied for the GOE matrix. And those are given by these Dyson-Schwinger equations, which come from quantum field theory and basically can be deduced from these Gaussian integration by parts formulas. So one of the reasons why we love the Gaussian is that it satisfies this very nice formula. The expectation of x times f of x is equal to the expectation of f prime of x for a polynomial f. OK, so what this leads to is things that look like the self-consistent equation for the semicircular law, but they have this extra correction term, which corresponds to the derivative. And this is the first order equation. And then we get further equations where we can write the original thing times products of the Stieltjes transform at other locations, that this is equal to some set of lower order terms. And what we actually show is that Q satisfies the same system of equations modulo some multiplicative constants up to some small error. So the example that has to do with the first equation is just if I look at Q minus YQ, once again, I multiply this factor, which has to do with the difference in density at the edge. Then I add the same correction factor. Then this self-consistent equation is satisfied at rates smaller than 1 over n eta, smaller than what we need to talk about individual eigenvalues.
So these are equations for GOE, or is it for the graph?
So the equations come from GOE, but the point is that Q, which comes from our graph, satisfies similar, basically the same type of equations. Yeah. So the point is that basically like the equation that we're looking at isn't this one specifically. It's this Q minus YQ, which is also satisfied by the GOE, right? But the point is that basically like modulo some extra factor, we can get the same thing to work.
But that is some other method because your integration by parts doesn't exist for regular graphs, right? So
oh yeah, this is just okay, but this quantity still makes sense, right? In the sense that like when I take the derivative of the Stieltjes transform, this is just going to be a product of two Green's function entries, right? And so really, I could just write this out to be like a formula to do with Green's function entries, which is more or less what we do.
So you use some other method to deduce this equation?
Yes. Yeah. We don't use this formula. This is good. Really, what we do is that we do this Watt counting argument again. So specifically, when we want to bound Q minus YQ, I'll just do one slide about this. I think about the Green's function after I do this resampling. So I fix some vertex J, and then I resample the neighborhood of J. So once again, I can use the Schur complement formula to basically write the Green's function at J in terms of the value at its neighbors. And I basically want to compare this to this other graph, which is just I have the vertex J, but instead of the rest of the graph, I'm just connected to two loops of weight Q. So the general idea is that I can basically expand this using the resolvent identity, and which is just talks about the difference between matrix inverses. And I can basically compare walks of different types. So once again, I want to compare walks that started in at a vertex. So I could start at a vertex, I could go out through this vertex, walk around, and then go back. And so in the left-hand graph, this would give me this contribution. On the right-hand graph, it would just look like Q. I could also talk about walks where I go out on a vertex, I walk around, come back through the other vertex, and then go there. So I get a contribution from the left-hand side, not the right-hand side. And then I have higher order terms. But the point is that I want each of these terms to cancel each other out. And the general idea is that if I've done a good job in randomly sampling the boundary, then the value that I get at a boundary is approximately the expectation over all edges in the graph, which is exactly what Q is, right? So basically, like the first order term here is going to be like exactly Q. And moreover, this is roughly like taking the average of all entries of my Green's function, which is going to be approximately equal to 0. We need to prove this rigorously, and actually a large portion of our proof is showing that these intuitive arguments are true on a much more rigorous level. Okay, so I'm out of time. So let me just quickly mention some potential future directions. I'm talking here about the edge. From a statistical physics perspective, it would be quite interesting to find universality for bulk statistics. So I'll say, too, that eigenvector statistics are interesting as well. So He, Huang, and Yao applied this universality result that we showed to show universality of edge eigenvectors as well. But knowledge about the bulk is completely unknown. And if you know what no-gap delocalization is, for example, that would be, I think, a very interesting problem for the random regular graph. I would also like to think about these techniques for more general polynomials, like what we're talking about in terms of strong convergence. For example, I think it would be like an interesting exercise to basically just use these techniques to prove that 83% of bipartite random graphs are Ramanujan. Right? And I think if you just go through the proof and use pretty much the exact same techniques, you'll be able to show that type of universality. Once you get to more complicated models, right, then it becomes more difficult. But I'm definitely very much interested in this. And I guess the last thing I'll mention is that we can think about random regular graphs as sparsifiers of the complete graph. So I'd also be interested in finding sparsifiers of other dense graphs, trying to use Green's function in terms of these types of techniques. And the point is that these types of techniques are quite flexible. For example, in recent work, I was able to generalize these to distributions over infinite graphs. So yeah, just to conclude, we get eigenvalue rigidity for all eigenvalues of random deregular graphs, Tracy-Whittem statistics for the edge. And to prove this, and most deregular graphs are Ramanujan, to show, we use the local Dyson-Schwinger equation and also a recursive formula for the Green's function. So that's all I wanted to say. Thanks.